So first of all, we came up with this construction of a graph to visualize some of the aspects that we think are of concern when talking about the complexity or the randomness of an object. So as you can see on the screen is a graph that we constructed recursively. And the way it is built is basically you start with 2 nodes. Basically, all the nodes that are colored in red are going to have exactly the same links as their label, right? So you can see we add a new extra node, and then this already has 1 link, which is related to the label it has, and this other one has 2 links, and you keep adding nodes in this way, so you complete the ones that they are already before with the number of links that that label is suggesting, right? So this has 2 links, this has now 3 links, and you always have like a remainder. So these are the blue nodes, and you keep going, and basically all the red ones are already completed. So this is a completely recursive deterministic graph. So if you run the algorithm again, you get exactly the same graph and the same distribution. But when you look at the representations of the object, they can be quite different. So we built this graph on purpose because actually the degree distribution sequence is of almost highest maximal entropy, just by the way it was constructed, right? Because actually what you're going to get at the end are all these labels corresponding to the degree distribution. So what you have at the end is a Chaperone number, which is Borel normal, and basically that's the definition of maximal entropy. If you are an observer, obviously, so you're an observer looking at the process unfolding, because if you already know that this graph comes from a deterministic source, then the entropy is 0, right? But that's not the problem. The problem here is what happens if you are an observer and you're looking at this process unfolding. Then you have different ways in which you can actually see the object. So if you look at the adjacency matrix, for example, it looks very regular. Right? So you have this shape that keeps growing, and basically the matrix is getting sparser and sparser. So actually the entropy looked at from the point of view of the adjacency matrix tends to 0 entropy, right? Because it is mostly empty, and then we have only a pattern in the middle. But again, if you look at the degree distribution, this is actually diverging. So the entropy of the degree distribution is reaching maximal entropy. So we already knew this, right? Because entropy is based on probability distributions, and you have to make an arbitrary choice on the object of interest. So depending on how you define the object that you are going through, basically, is how you would represent the classical information content of that object. And that is basically because there's no invariance theorem independent of a language. So actually the graph comes from a very short program, and this is a program written in the Wolfram language, which is pretty cool because it is very nested. And these basically 2 lines of code reproduce the whole graph. And that's the way we actually know that this is very low random, because it is created with a short computer program. And that's actually the idea of behind Kolmogorov complexity, right? Or algorithmic complexity. And the idea is that you can actually say something more interesting about sequences like these ones, that if you're an observer, you may assign a high algorithmic, a high randomness degree, but actually it is a low algorithmic random because they are reproduced by short computer programs. So this is a tumor sequence that we, I think it was yesterday or before yesterday that someone talked about it, and it is very easy to construct, so it's recursive, and the same for pi in binary. So pi has many short representations. And you want to say something interesting about these sequences in the sense that they are produced by something mechanistic. And the way to do so is basically with algorithmic complexity. So what you look for is the shortest computer program that's running on a universal Turing machine reproduces the original object. In this case, S will be any of these sequences. And the power of algorithmic complexity, as most of you here probably know, is that it is not any definition of randomness. So actually in the 60s, many people tried to come up with a definition, precise mathematical definition of randomness. And it turned out that all of them were equivalent in a very strong way, except for some non-constructive definitions. So there are levels of randomness, but at least for the first level, most of them or all of them coincide. And that is basically what is known as the convergence of definitions, and that happens sometimes in mathematics. The same with the Turing machine, when others like George and Post and other people came up with the idea of computation, and they showed that they were definitions equivalent to each other. And that's because they capture something fundamental. So actually, the most important problem of these measures is that they are semi-computable, in this case, lower semi-computable, and that means that we can approximate it from above, but it is not completely computable. There's no algorithm that gives you the precise answer. So this is very numerical. It is basically suggesting you can try to calculate it, but you will never reach the ultimate answer. And that has prevented people to actually come up with applications, and most people use lossless compression algorithms, but we are going to see that they represent a lot of trouble. So actually the most important problem for applications is what is the invariance theorem, that basically tells you that if you change the reference universal Turing machine, you are going to have convergent values in complexity. And the values are actually not, do not depend on the choice of optimal universal Turing machine. But the problem is, and the negative reading of this is that you don't know how fast the convergence happens. And it could be that at the beginning you have all these are a sketch of what could be happening before actually converging. And this will be the best case. If C were converging to 0, but it could happen anything before that, and we never know. But we can have some sort of idea, perhaps, if we look at it from a statistical perspective. So there's a lot of people that have chosen to go with popular lossless compression algorithms. And this is some sort of a landmark paper in the area in 2005, where they were able to reproduce phylogenetic trees by looking at the compressed ratio of full genomes. And the interesting thing is that they came up with basically the exact biological phylogenetic tree that corresponds to what is known in biology. But one problem, there are two problems here. Is one, that there was no kind of control experiment, because actually it is known in genetics that to come up with this phylogenetic tree is almost trivial if you look at what is called GC content. So basically, if two species are related to each other, they would have about the same number of G and C nucleotides. And it is basically almost like an evening experiment to come up with. And you don't need anything like a lossless compression algorithm. You just need entropy or even just a counting function to reproduce this. Nevertheless, this basically tells that compression works as expected. Popular lossless compression algorithms work as entropy rate estimators. Right? But the problem is to relate that to algorithmic complexity, and that has been a problem from my perspective in the field. So there's another example here. This is even more interesting because this was published in a very important journal, Science Translational Medicine, which is a subjournal of science, and they were proposing a measure of integrated information for consciousness. Suddenly, at the middle of the paper, they jump to compression. So they used Lempep-Siv, basically. And they related to integration with no justification, and then even to algorithmic complexity. So this is all over the place all the time. And most of the time, it is very obscure how they make these connections. So is there any way to actually do better than practical lossless compression? And this is what we came up with a few years ago, like 10 years ago or even more. And the idea is to use the idea of algorithmic probability. So you may remember this infinite monkey theorem from Emile Borel, where it is kind of a whimsical thing that when you are typing on a typewriter and you have a source of randomness, which is here represented by a monkey, you waiting long enough, you can reproduce anything with a structure, even the works of Hamlet, of Shakespeare, let's say Hamlet, for example. But if you actually do the math, it turns out that it is many times the age of the universe. So how it comes that actually we can produce these things in shorter periods, and things change dramatically when you change a typewriter by a computer. Because now the question is, you don't have to reproduce things like all the digits of pi, for example. You just need to reproduce the formula that reproduces the digits of pi. The same for the works of Shakespeare, right? You don't have to get Hamlet right letter by letter. What you have to do is something that gives you perhaps a human being that perhaps looks more complicated, but actually it is not, because that shortcuts basically the time that you need to reproduce something like Hamlet if you only have the age of the universe, for example. So this is a very beautiful theory that is called algorithmic probability, and the idea is basically what I just said. So if you are looking for reproducing objects that have a lot of structure, in other words, they are low algorithmic random, then they have short descriptions. And that means basically that by chance, you can type the right formula that reproduces the whole object, instead of having to type every piece of the object. And that is called algorithmic probability. And the formal connection between algorithmic probability and algorithmic complexity is given by what is called the coding theorem. So based on this, what we did was actually to run an experiment that has been going out for years. And the idea is that basically you start with small computer programs running one by one with a universal enumeration from shortest program to longer program. And for a few computer programs, the problem is decidable. For example, if you have the busy beavers for Turing machines, then you can go one by one. And if you see that the Turing machine doesn't halt by the time of the busy beaver, you know that it will never halt. So you don't increase the counter. So what we are trying to do here is to reproduce what is called a universal distribution. So we count how many times every output has been produced by all the previous Turing machines that have been explored. And then you can exhaust the size of the Turing machines that goes by, let's say, the number of states. Also, you can slice it in smaller pieces. But you can just increase the number of states, and then you have an exponentially larger space, and then you go through them. And obviously, eventually you reach undecidability, and what you do is to take educated runtime guesses. So basically, it is an inverse exponential function as a function of runtime. So the longer it takes, the less probable it is to halt. But you can just set a threshold, and basically once you run through all those runtimes, you rerun all the Turing machines to the next runtime. So it's dovetailing basically. And then we have two ways actually to measure algorithmic complexity. One is through algorithmic probability. So we use the coding theorem to get back to algorithmic complexity. Or we can actually find the first shortest computer program that produces that string, and then we can actually compare the two measures, and basically they correspond perfectly. And this is only one test of many that we have done with this, just because it is very interesting to see how it behaves. But beyond algorithmic complexity, we think this is a very interesting way to actually find generative models. So for the problem of causal discovery, because what we are basically creating is a framework that allows you to find computable models of data that you may find in nature or anywhere else. So before, if you want to, for example, measure the entropy of a sequence like this one, obviously, again, if you want to cheat, and that's always the point, right? The expected value of entropy should equal algorithmic complexity. But if you're an observer, entropy doesn't give you the tools to actually be able to calculate these things. And in this case, it's very simple because it is just the sequence of natural numbers. But in general, this could be much more complicated, and you wouldn't be able to find the algorithm producing the sequence. But with this procedure, basically, by exhausting and performing a search, an exhaustive search, you can find the programs that can generate this sequence. And for this one, for example, it's very easy. Either in binary or unary, you can find the programs that produce this sequence in decimal. And actually, this conforms also with the theory when you plot the distribution of complexity values. So this is what you would find in a textbook for Shannon entropy. So it is a Bernoulli distribution when you take all the strings up to certain size and then you plot by number of ones density, and you have basically this curve. And then if you compare to lossless compression algorithms that reproduce exactly the same curve, and that's exactly because what I said before, popular lossless compression algorithms like Lempel-Sieve are just entropy rate estimators. So it is very difficult to make a case that actually they are related to algorithmic complexity other than how Shannon entropy is related to algorithmic complexity. But then we have what we call the BDM method, which is based on what I just said. So we call it CTM, the part that is the Coding Theorem Method. And then BDM is a way to actually expand the power of CTM by combining it with Shannon entropy, but still you carry out local estimations of algorithmic complexity. And what you get is this distribution with these gaps that I used to call causal gaps, because basically it means that we have found for some of these elements a computer program that is giving or assigning a lower randomness estimation than Shannon entropy. And actually we have here, for example, two instances of strings that would have maximal entropy, but actually have lower algorithmic complexity. So you may say, oh, this is perhaps relevant only for during universal systems, and maybe nature is not, in nature is not that relevant, but actually we have proven that at least 60% of the simplicity bias from the output distribution of other computer models in the Chomsky hierarchy can be explained with the universal distribution or algorithmic probability. So it is relevant to most of these levels of computer power. So how it works? So this is an oversimplification because this is a very high level introduction. So let's say we have a picture of something that is highly causal. So what we look is to look at little pieces of what we call causal patches that we can explain with the small computer programs. And that would give an indication of whether this process is random or not. And actually the algorithm is more complicated than this because it is actually traversing the whole thing looking for small algorithmic patches. And there's a lot of technicalities here because obviously how you deal with the boundaries and those kind of things. But we have a 40-page paper actually studying those considerations. So what is algorithmic information dynamics? So basically, is exploiting now these two tools that we have to explore the space of computable models. And actually, algorithmic information dynamics is independent of these numerical tools that I was talking about. But again, if you use, for example, popular lossless compression algorithms, you wouldn't really be exploiting the power of algorithmic complexity. And actually, you wouldn't even be able to do anything interesting because we are talking about, for example, small perturbations. And lossless compression algorithms are not sensitive enough to deal with those ones. So let's say we have, for example, these two strings and you just flip one bit. If you compress these two sequences, it is very likely that using any popular lossless compression algorithm, you are going to get exactly the same compression size. Because a lot of reasons, they have checksums and those kind of things. Obviously, you can simplify the compression algorithm and perhaps do something about it. But in general, it will be very difficult to make lossless compression algorithms to deal with very short changes. So the idea is basically this one. So let's say you have a very structured sequence and then you make a random perturbation and you flip a bit. Then you look at what happens with the algorithmic explanation. So basically the computer programs that you can find that are able to explain these two strings, the original one and the mutated one. And what you will find, for example, in this case, because this, I think this could be computable for this particular case, you can immediately recognize that this is highly compressible. But if you introduce this random flip, then you have to account in your computer program that explains this one for the change that we introduced. So the original model is going to increase in size, so that the algorithmic complexity is going to change, right? So it is basically an interventionist numerical framework that is able to deal with this kind of cases. And here are some other examples. So this is again highly compressible. So it is just an iteration producing once. But if you introduce something else, then you have to account for it. So the compressed form is going to be larger than the original one. And then there are all sorts of interesting facts. Like, for example, if you start from a random object, if you perform a random perturbation on a random object, basically it remains almost the same compressed size, right? Because you still have to account for those 2 digits in the beginning because they were random. So if you perform something random again, it doesn't matter. So there's no changes. And you can translate this into all sorts of interesting questions. So you can now deal, for example, with graphs, because we know that the algorithmic complexity of very simple graphs, like complete or completely disconnected graph, grows by the logarithm of the number of nodes. So it increases in size very slowly. But if it is a random graph, then because you have to account and give the precise location or connection of each link, then we know that the algorithmic complexity grows by the number of edges, perhaps divided by 2, because the location of one may give you some indication of the next one. But now if you make perturbations, then you can also see how it works for graphs. So you can explain this one with a very short computer program. And actually this computer program basically explains all the complete graphs, not only this one. But if you keep adding more nodes, basically it's the same computer program, right? And with a random graph, then, as I said, because you have to specify every link, then it grows by the number of links. And we know that complex networks basically are between these 2 cases. And the program size is exactly between these 2 cases. And then when you perform perturbations, then you can do all sorts of things. So actually how we measure the complexity of a graph, what we do is to look at the adjacency matrix and then define a termite, a two-dimensional Turing machine. So this is a 2-dimensional complexity measure, native in 2 dimensions. And the question is, in terms of algorithmic probabilities, how likely is to reproduce the adjacency matrix of a given graph with a random Turing machine. Now the question is not that simple, obviously, because an unlabeled graph can have many representations, many adjacency matrices. But what we have also proved, and it is not very difficult, both theoretically and numerically, is that any representation is a good representation of the automorphism group. And here is the definition with automorphism group, but basically means that also if you only get one, it is a good representation of the group. But again, you can do now small perturbations to the elements of the graph. And what you have is something like we call information spectra, because now we know exactly the algorithmic information contribution of every element of the graph to the original graph, right? So by deleting this graph and then looking at the models that are able to explain the new graph with the perturbation, we know how much was the contribution of this element to the original graph. And again, as I said, popular lossless compression algorithms wouldn't be able to deal with these things, because as you can see, actually the adjacency matrix of this thing is always the same, even if we flip bits, nodes on and off, for example. So this is a representation of what is going on. So basically we have a space of what I call platonic space of computer programs. It is platonic because you never can really reach it, right? It is uncomputable in general, so you can only make approximations. And then you have what we call a BDM mapping. So if you have a piece of data, because you cannot find the computer program that explains the whole data because it is too large, and most likely very difficult to find the program that exactly finds that piece of data, what you do is to decompose the original data, and that's why it is called block decomposition method. So what you have at the end is that little pieces correspond to different programs in the program space. And some pieces,
5 minutes left.
Thanks, Narcissus. So some pieces may be explained with computer programs that are larger than other places of the same piece of data. And the piece of data can be anything, by the way. It could be the output of a dynamic system evolving over time, for example. So what you have is some sort of surface. This surface is just a sketch because it is not corresponding with the colors, right? But let's say that we had in this axis randomness, then you would have some sort of surface and something that we call the reprogrammability landscape, because basically it tells you which points you can modify in your original data to make this data less or more random. So this is a toy example that we are developing in the next few months further for another publication. But let me explain it. So we have elementary cellular automata on this side. So this is the original versions, what I would call the ground truth. And then let's say that we scramble the rows. I'm not showing the scrambled version because you can imagine how it looks like. It didn't make sense. And we did it exhaustively. So actually we take all the scrambling permutations. And then we try to reconstruct that original picture of the space-time evolution of the cellular automaton by taking the configuration that has lowest algorithmic complexity. And you wouldn't be surprised, right? Because, for example, in this case, it is clear that if you put the blocks together, you can explain these three things, for example, with a very simple computer programming. But there are some less obvious cases, like this one, which doesn't look that far from the original one. And actually, if you take the Pearson correlation, it's very high and significant. Perhaps in this case, in particular, is not that high. Also, qualitatively, you can see actually there's some correspondence. But with others, it is quite high. So, for example, rule 54. So obviously, the more random looking is more difficult to reconstruct, but you can see the idea of how this works. And this can be improved, obviously, by just running more computer programs. So this was with a small space. And in some cases, actually, we took, for example, the cases in which we had the same configuration in the right way, but I didn't want to pick the right one. So actually, we got it exactly right, but I picked the one that looked like flipped. But the interesting thing is this one, because in this one, we don't have any idea of, once we reconstruct, we don't have a time index, right? We just reconstruct the whole object. But the interesting thing will be, can we reconstruct how this thing is actually evolving? And it turns out that we can also say interesting things. So we have, again, the ground truth, and then we can come up with models or hypotheses by performing these experiments. And we come up with these results. And you can see again that actually this is, for example, highly significant. And basically here there's an index. And what we do is to perturb every possible row and then look at the models that can explain those ones and which ones minimize explaining one model from the next one. And basically what we have is a sequence of models that give us the time index of this cellular automata.
2 minutes left.
Thanks. And that's pretty much it. So thank you very much.
Thank you, Hector. We might be able to squeeze one question. And obviously you can continue and ask your questions in a chat.
Absolutely. So I can see some questions now here. So is this presentation shared somewhere? Yes, I can make it available. And I think we recorded this, so we can also put this video perhaps. What software could you recommend? So we have a complexity calculator online, and there are several libraries now in several languages, Python and R. So actually in R is native, so you can just call it directly.